So in this lesson, rational functions and graphs, we're going to take a deeper dive into what the graphs look like for various rational functions. So far, we looked at the most simple case, the reciprocal function, right, where we had two branches and a vertical and horizontal asymptote. So let's take a look at what we're going to see in this lesson. And then we're actually going to break this into two parts. Okay, it's fairly complex, probably the most complex lesson of this unit. So we're going to first look today at how do we find the vertical asymptotes for a given rational function. And it's also something called a hole. Okay, so that will be the focus of today's lesson. The other two objectives we will get to in the next lesson. Horizontal asymptotes, and then looking at what the graphs actually look like. All right, so we're going to formally define a rational function a little differently than the way we've described it so far. We're going to say that it can be written as the ratio of two polynomial functions. Now, polynomial is just a big math word for two or more terms, or even just one or more terms. So it has multiple terms in each expression. Okay, so that means we can have variables like x in both an expression in the numerator and an expression in the denominator. Okay. Now, one comment here, it says the domain of f of x is all real numbers except those where q of x equals 0. So notice q of x is in the denominator. And once again, we know we cannot divide by 0. That's going to actually be a very important concept as we move forward here. So here's some examples of rational functions, right? So these look a lot more complex, right, than the simple reciprocal function we've worked with so far. But let's see if we could identify, right, what p of x is in the numerator and q of x, what those functions are. So in this example, right, negative 2 times x would be p of x, and q of x would be x squared plus 2. Okay, those are the two functions that make up the rational function. Let's look at another example here. P of x is just simply 1, a constant, and q of x is x squared minus 4, a quadratic expression. Let's look at one more example. Here we have an expression or a function that is in factored form, x plus 2 and x minus 1 for p of x, and just simply x plus 1 for q of x. Okay, so that's what we mean by describing a rational function as a ratio of two functions, each of them having x as its variable or simply a constant. All right, now what about this concept of domain restrictions, right? We have said that we cannot allow the denominator q of x to be equal to 0. So here's another way of showing that, right? X squared plus 1 cannot be equal to 0. That equal sign with a slash through it means not equal. So if we were to solve for this and figure out what values of x would make that whole expression equal to 0, we would do the normal thing, right? We're going to subtract 1 from both sides. But notice we wind up with x squared cannot be equal to negative 1. Now, there's no real number, right? If we square it, it will give us negative 1. We would get an imaginary number, but not a real number. So in this case, there is no real value of x that would make the denominator equal to 0. So there's no restrictions on the domain in terms of real values. Now, if we were to graph that, and don't worry about what this graph actually looks like or how we came up with that, right? We would see kind of an odd looking graph here that I'm showing below. And it goes from negative infinity to positive infinity, but has kind of a unique curve to it right around the origin. So one word we're going to use to describe a graph like this is that it's continuous, meaning it has no breaks, jumps, or holes. We'll define what a hole is here a little bit later. So if you think about that first reciprocal function that had two branches, right? The graph is broken into two parts. So that would have breaks or jumps in the graph. Okay, but if it's continuous, then what we're saying is it has no vertical asymptotes. Remember, our goal here is to be able to identify where the vertical asymptotes are for a given function. All right, let's look at another example. F of x equals 1 over x squared minus 4. So same thing, we cannot let the denominator x squared minus 4 equal to 0. So to find the values of x that would make it equal to 0, we're basically going to solve it. So we're going to add 4 to both sides. And now we see that there are two real values, positive 2 and negative 2, that if we put them in for x would make the denominator equal to 0. So what does the graph of that look like? Notice now we have 3 branches, right? 3 different graphs broken up into 3 parts here, or curves, I should say, and divided by asymptotes. Notice that there are 2 vertical asymptotes in this function, okay? Now, where are those asymptotes? Notice they are at -2 and +2. So where we're headed with this is that the domain restrictions on x that make the denominator equal to 0, that is where we're going to have breaks in our graph or curves, and that is where we're going to have a asymptote. So this function that we just looked at, the second example, we would say that it has 2 points of discontinuity, 2 places where the curve is broken, and those exist at x equals 2 and x equals -2. All right, let's just look at a few graphs here and see if we can determine whether they are continuous or discontinuous. So remember, discontinuous means there is a break. We're going to have 2 or more branches. Continuous means there will just be a single curve on the graph. Okay, so for A, we can clearly see that there are 2 branches, therefore it's discontinuous. And where are those points of discontinuity? Well, where is the vertical asymptote? It's at x equals -1. Okay, let's look at another one. Here we can see 3 branches, right? So we have 2 points of discontinuity, and those are going to occur at x equals -2 and x equals 1, where the vertical asymptotes are. How about C? Well, that one's pretty clear, right? There are no breaks that we can see, at least in the range of values that are being graphed here. So we would say this is continuous. So if it's continuous, then there are no points of discontinuity. All right. So let's summarize this. To find the points of discontinuity, we find the values of x that make the denominator equal to 0. Okay, so let's look at another example without having to actually see the graph. Could we identify the points of discontinuity? So we want to set the denominator equal to 0. Now notice, in this case, q of x is a quadratic expression, quadratic function. So how do we solve a quadratic equation? We have to set the factors equal to 0. So let's factor that, right? X plus 1 and x plus 2. And if we were to solve for x, right, we would see we get 2 values, either x equals -1 or x equals -2. Either of those values would make the entire denominator equal to 0. So how would we say this? We say there are 2 points of discontinuity at x equals -1 and x equals -2. All right, let's try another example here. So same thing, we have a quadratic, right? Let's factor that. We have x plus 1 and x plus 1 factors pretty easily. And so in this case, we really just have 1 point of discontinuity, right? Because we get the same value, -1, for both factors. So here we would say there is just 1 point of discontinuity at x equals -1. Okay, we don't need to count the same value twice. All right, well, let's look at another example here now. So set the denominator equal to 0, right? We have x squared plus 1 equals 0. This is similar to what we looked at before, right? If we solve this, we get x squared equals to -1. And so x would be equal to the square root of -1, which is not a real number, right? This is I, imaginary number. So here we would say there is no point of discontinuity. This would be a continuous function. All right, now let's talk a little more about the difference between an asymptote and a hole, right? We know how to find these points of discontinuity, but those points can either be an asymptote or a hole. Okay, so what's the difference between the two? Well, let's go back to this function, right, that we saw before. We had two zeros. Now, zeros are the values of x that make the denominator equal to 0, right? We had two zeros at x equals 1 and x equals -2, and that's where we had our vertical asymptotes. Here's another function. And notice when we graph this, and again, I wouldn't expect you to know how to graph this. I'm just going to give you the graph to help you understand the difference here between an asymptote and a hole. Here we see it actually becomes a linear graph if we simplify it, but notice there is a circle or hole at x equals 2. That is what we call a hole. Now, why is it a hole and not a asymptote? It's because the 0 for the denominator, +2, is also a 0 for the numerator. Okay, so if we have the same value that makes both the numerator and the denominator equal to 0, if we plug it in for x, then that value is going to give us a hole. It's a little different than an asymptote. Okay, so when we simplify it, right, we cancel out the factor x minus 2, we're just left with y equals x plus 1, which is a linear equation. And it looks like it would be continuous except for at x equals 2. That's where we're going to place a hole, and that's shown by an open circle on the graph. All right, so here's the final summary of this. The rational function f of x is equal to the ratio, right, of p of x of q of x, and it has a point of discontinuity for each real zero of q of x. Remember, real zeros are the values of x that make the denominator equal to 0. So if they have no common zeros, meaning the values only make the denominator equal to 0, then we're going to have an asymptote at that point. If they have a common 0, then we're going to have a hole at that point. In other words, if there's a value that makes both the numerator and the denominator equal to 0, then that will give us a hole. All right, so let's look at a few examples here, right? These are already factored, so it's really easy for us to figure out what the zeros are, right? Here we would have an asymptote at +2 and -4. In the numerator, the 0 would be -3, so it's not common, it's not the same as 2 or -4. So both of those points of discontinuity would be an asymptote. Now here's an example where we do have a hole, right? We actually have one of each, right? We have a hole at x equals negative or +2, because if we put that into either the numerator or the denominator, it's going to make it equal to 0. And then we have a unique hole, or a 0 rather, at x equals 1, so that will give us a vertical asymptote. Okay, kind of confusing, but let's look at a couple more examples here. All right, so here's what I'm going to ask you to do. Describe the vertical asymptote in holes. Okay, so the first step, right, is identify the zeros for p of x, the numerator, and q of x, the denominator. So for p of x, right, if we put in -1, that would make it equal to 0. So we have a 0 of x equals -1 for p of x. For q of x, we have it at 2 and 3. Now, are the zeros of p of x the same or common with the zeros of q of x? No, they're not, right? -1 is a different value than 2 or 3. So what that means is we can ignore the 0 in p of x and simply say that the two points of discontinuity at x equals 2 and x equals 3 will be vertical asymptotes. Okay, so we would say two vertical asymptotes at x equals 2 and x equals 3. All right, let's try another one. So same thing, let's find our zeros first. So we have 2 and 1 in the numerator, p of x, and we also have 2 in q of x. So what does that mean? We have one point of discontinuity, it's at x equals 2. Now, is that going to be a whole or a vertical asymptote? Well, it's common, right? 2 makes both the numerator and the denominator equal to 0. So we would say that in this case, our point of discontinuity at x equals 2 is a whole because it's common with the 0 in the numerator. All right, let's try another one here. Boy, this one looks really messy, but it's not too bad, right? Same process, p of x. So our zeros are going to be at 3 and -4. Q of x, we have +3. We actually have it twice. We only need to list it once. And a +4. Okay, so remember, the points of discontinuity will always come from Q of x. They're at 3 and 4. The question is, are they asymptotes or wholes? Well, we have one common 0, x equals 3, right? So that will give us a whole. And we have one unique 0 at x equals 4. That will give us a vertical asymptote. So here we would say we have a whole at x equals 3, and we have a vertical asymptote at x equals 4. So one of each. All right, let's do a couple more. See if you can figure out where the points of discontinuity are and whether they are a vertical asymptote or a whole. So pause it, see if you can figure that out, and then continue to see the answer. So we're going to solve for x. It's a quadratic, but we can simply solve for it, right, by adding 16 to both sides, and we get +4 and -4. So we would say there are 2 vertical asymptotes at x equals 4 and -4. Notice, since we just have 1 in the numerator, there are no zeros. We don't have to worry about there being a whole. All right, let's try another one. So in this case, right, we get x squared equals -3. We've seen this a few times. What are we going to say? We're going to say there are no real values of x that would make the denominator 0. Therefore, there are no points of discontinuity. All right, let's do another one here. Quadratic. We're going to have to factor it, okay? So if we factor that, we get x minus 2, x plus 4. Notice the 0 in the numerator, x plus 1, would be -1. So we're not going to have any common zeros here. Both of these will be vertical asymptotes. Okay, so that's it for now, right? The first half of this lesson, we know how to find the vertical asymptotes and wholes by finding the zeros, the value of x that makes the denominator equal to 0. And if that same value also makes the numerator equal to 0, then that gives us a whole. All right, that's it for now.